Okay, now we will look into enclosure itself from the outside to the infrastructure that keeps the system safe, serviceable, and compliant. And we'll be looking into 20-feet container, but generally approach in customized it will be the same. The same things, maybe a little bit smaller, but the whole approach will be the same. Then since 20 feet is the most popular, we'll be looking into 5 megawatt hour 20 feet container, workhorse of the current generation of battery energy stations. So at the top we see liquid cooled HVAC system or air conditioner. Its job, as you can see from the name, thermal control during operations. It keeps cell temperature uniform and it improves lifetime, efficiency and reliability of battery energy storage system. Next, exhaust system, exhaust fan, and it will be NFPA 69 compliant. We'll talk about fire safety in our hot topics because it's very important. But as for now, we need to understand that we have this emergency exhaust fan. It's designed for rapid removal of flammable and toxic gases, such as hydrogen and carbon monoxide, in case of thermal runaway event. So if anything goes bad in the battery and there will be a fire, it should remove these gases. So it's gas management, not a fire suppression. And it's a key safety layer of modern battery energy storage system. And as I mentioned, it's requirement of NFPA 69 compliance. Then we have like air inlet. Again, NFPA 69 compliant. So it's support control airflow. It allows inflow of air. So in the case of emergency ventilation events, it ensures that we have exhaust of air and at the same time we have air coming inside, so we can quickly remove the gases and replace them with air from the outside. Next is fire alarm devices. So they are mounted externally. It's audible, visual, like beeping alarms. So it's sounders, lights and bell. And the role is simple. Alert people nearby and signal abnormal conditions inside the enclosure. So next one is external fire control box. This is box for the human interface to the fire system. It typically includes an emergency stop button. So like you press it and everything stopped, disconnected. And the manual fire initiation system. This allows fire responders or operators to interact with the system without opening enclosures because we don't know what's inside. And of course, battery doors. So it's access door to provides entry to the internal compartments. Now we will open these doors and look inside. When we open them, you can see battery models with BMU. This BMU will measure like cell voltages, temperatures, but BMU doesn't control it, just can take information. And next, there is like one group of batteries. So it will have connection to BCU, as we discussed when we talked about racks. Again, this BCU voltage box. So it serves as DC disconnector. It has fuses, contactors, and string level protection. So it allows safe isolation and protection of the batteries, as we discussed. Next, we have like sensors. They are very important. You can see here, but on the top there will be hydrogen, carbon monoxide, temperature and smoke detection. So it's allow for early detection, catching of gases when abnormal behavior just starting even before the fire. And we'll look into this a little bit later in this part. In top of some of the enclosures, we also can have like defragration panel. It's NFPA 68 design, not 69 but 68. And this is a passive safety device. They are not doing any fire suppression. The function is that if inside the container pressure rapidly builds up, due to gas ignitions, these panels will open in a controlled way to release this pressure. And you can look at it if, for example, there will be explosion inside the container, because we have like hydrogen generation. It will release this pressure on top instead of front. And why it's needed? Because imagine situation, you have hydrogen inside, and there is like fire marshal or somebody is opening the doors. So when he will start opening the doors and there will be a mix between hydrogen and oxygen, you will get explosion. So this person who will start opening the door, so he might be well injured because of this explosion. So what we want to achieve, if it happens, the gas will not open the doors and will get this person away, but the gas will and explosion will go on top instead of front. So it's more like for passive system for human safety. So we'll talk about design for NFPA 68 and 69 in hot topics, but it's general approach. Next, we have low voltage distribution box, where we have like all auxiliary system connections, and that helps provide power to communication to BMS, and UPS. It could be on the back or somewhere around, and UPS is provide the power backup for all these sensors and BMS for some time if the enclosure will not have power. And finally, we have DMC box. That's designed for external DC connections. So that's a box where we'll have this container connected to our PCS. Inside the DMC box or near it, there could be like fire control panel where all the gas sensors will be connected. So it will do coordination, and usually it's placed near DMC box or in the low voltage box. So that's all about typical design. Again, if it's 20 feet container, 5 megawatt hours, there could be small differences, but generally it will be approach. And if we look into customized solution, it will have all the same components. They could be placed differently, like much smaller HVAC and so on, but general approach and general components will stay the same. So yeah, thank you for watching for this video, and see you in next one.